Okay, let's get started, please. Okay. I'm not sure where. I thought people were missing on Monday because of the rain. Maybe they're missing today because of the sun, or I don't know. Okay, in any case, you are here. That's great, those of you who aren't here. Remember what we're talking about? We're talking about infinite series. And the last thing we mentioned was we talked about power series and the radius of convergence, right? Which is something that will be very, very useful to you when you take a course, if and when, or when you take a course in complex analysis. Okay, so we're going to talk today about kind of a particular kind of series, so series of the form summation a sub n b sub n. Okay, so like you have two, right? You've got two sequences. You take the product of those sequences, and then you take the sum. Okay, and this will be we'll have various examples of this, which will be useful. Okay, so one useful lemma will be the following: partial summation. We're going to call it a partial summation formula. Okay, so here's what it says. Suppose you have two sequences, a sub n and b sub n. There's some sequences. Okay, and we're going to notate capital A sub -1 as 0. And capital A sub n for n bigger than 0 as the summation as the partial sum from a0 to an. So this is for n bigger than 0. Okay, so this is just the partial sum. Okay, and this notation we'll use for a short while. So okay, so the claim is the following, that if you're looking at this this kind of series that we're thinking about today, and you look at part of the tail, okay, so sum from one point to another. Okay, so you're taking the sum, you're taking some chopped off, some truncated portion of the tail, okay, of this series. Then there's kind of a useful expression, and it goes like this. That you can express this thing as a sub n, so the sum from n to p, from p to q minus 1 of capital A sub n times b sub n minus b sub n plus 1 plus a sub q, capital A sub q, b sub q minus capital A sub p minus 1, b sub p. Okay, that is, you can express this tail with this expression that involves the partial sums of one of the series. Okay. Okay. So this is not a particularly exciting formula, but it will be very useful. Okay. Okay. In any case, let's get to the proof of it. Okay. So the proof is as you might expect, not particularly exciting. So let's just look at the right-hand side. So we've got this thing here. And we're just going to mess around with it and then end up with this thing here. Okay, it's not the most exciting proof. Okay, so what we do first is we're just going to split this first term up into two parts. Okay, so let's say this is the sum of a sub n, b sub n from n equals p to q minus 1. We're gonna put in this term, the aq dq term, and then we subtract off the second part here, right? We subtract off the second part here, a sub n plus 1, again going from p to q minus 1, right? And we subtract off the last term. Okay. So we haven't done anything special. All we did was just separate this thing into two parts. Okay. Everybody all right? Yes. Yes. Thank you. Okay. So So what do we do now? We're going to combine things together. So let's right. This goes up to q minus 1, but we've got the qth term here. So let's just combine it together. This is n from p to q now, right? A sub n, b sub n, right? So we take these guys and put them together, and we do something similar for these guys, right? Here, the bottom term is a sub p, b sub p plus 1, right? So we're going to go one step down from there. So we go down to n equals p minus 1 to q minus 1, a sub n, b sub n plus 1, right? So we're just combining, right? Absorbing this thing into here and absorbing this thing into here. Okay. Right. Okay. So let's see what we do next. Again, nothing too exciting. We don't do anything to the first term, and we re-index the second so that it goes from p to q. Okay. So we're going to increase the index by 1. Right? And so we have to decrease it here by 1 also. Okay? So we're just re-indexing the second term, and then we combine them together, right? They're both now they're both going over the same range from p to q, right? So we get summation n equals p to q, a sub n minus a sub n minus 1, b sub n. Right? And, but this is the partial sum up to the nth term. So when we subtract the partial sum up to the n minus 1th term, we just end up with the top term, right? And so we end up with what we desire, summation a sub b sub n from n equals p. Okay. Any questions about that? Okay, so it's not the most exciting thing, but we'll use it to get a bunch of theorems. Okay, so okay, so the first result we're going to get, right? We're interested in series of this form. So now that we've got the lemma, let's get a result about that sort of series. Okay. So it says the following, that if so using the same notation as before, so saying we've got a sub n, b sub n. We've got capital A sub n as before. Okay. So if the partial sums are bounded, two, the b's are decreasing. So b naught is greater than or equal to b1, greater than or equal to b2, and so on and so forth. And 3, the limit of the b sub n is 0 as n goes to infinity. Then the sum of the a sub n, b sub n converges. notice that the infinite series, neither of these infinite series has to converge independently, right? Summation a sub n doesn't necessarily converge, right? All we're saying is that its partial sum series is bounded. Okay, its partial sum series is bounded, and then this other guy we don't know much either. It's just a sum of a decreasing sequence that decreases to 0. Okay, so we don't know too much about the convergence of the series separately, but we don't have to. We're getting a result about the sum of the product terms. Okay. Okay. So and again, this is you might think like what's the point of this theorem? Like the lemma was kind of technical, and the technical lemma gives us kind of a technical theorem. But this theorem is more like a tool that we're going to use. Okay, so you think of it more as a tool that you use to get other theorems. Okay. Okay. So okay. So let's think. Right, we want to show that summation a sub n b sub n converges. Right. Okay, so how do we show that a series converges? How do we show that a series converges? What's our sort of our main tool? Yeah, okay, sure. The sequence of the partial sums converges. Yeah, that will do, but I guess this question is too broad. Let me just tell you. So we're going to use the Koshi Criterion. Okay, Koshi Criterion is kind of one of the major tools to show these sorts of theoretical results. Okay, so we use the Koshi Criterion. Koshi Criterion says that this thing converges if and only if what happens? Anybody remember the Koshi Criterion? Anybody remember the Koshi Criterion? Mo, you're looking at me? Yeah, go ahead.
The diameter of the tail goes to 0.
The diameter of the tail goes to 0, exactly, right? So let me phrase it in the epsilon language. So it says that given any epsilon, there exists some point, let me make my notation consistent, there exists some time such that if you're past that time, if this is true, then the size of the tail, right, the size of the truncated tail, and Bn from n equals p to q is smaller than epsilon. Right? So we can make the truncated tail as small as we want, right? If we're given control over when that truncated tail begins. Okay. Okay. And you see why the technical lemma is going to be helpful, right? Because the technical lemma tells us exactly how to control this truncated tail. Okay. Okay. So let's look at it. Say, okay, well, we know that so fix an epsilon, right? And we're gonna try to choose an n. We'll try to choose the right n. Okay. So we have to think about it a little bit. We say, okay, well, think. Right? If we're looking at this tail, summation a sub n from n equals p to q, well, we have the technical lemma, right? The technical lemma says that this is equal to just the summation of a sub n b sub n minus b sub n plus 1 plus a sub q b sub q minus a sub p sub 1 b sub p. Right? And this goes from p to p to q minus 1. Okay? right? So, as an analyst, one of your first moves is to use the triangle inequality. So we're trying to get control over the size of this thing, right? It's the absolute value of the sum, so we're going to try to control it using the triangle inequality. And I think I've told you that I have a friend who hates the triangle inequality. Yes? Yes. Yeah. Actually, he doesn't speak to me anymore, but it's not because I use the triangle inequality. That would be great, but no, that's not the story. Okay. Well, sorry, Leibniz, we're going to use the triangle inequality. So here we go, right? They say, okay, well, look, we're going to control. We can control each of these things, right? The absolute value of the sum is controlled by the sum of the absolute values, right? So we're going to just put absolute values on everything, right? Okay, right, and just by the properties, if you don't mind, I'm just going to put, just by the properties of absolute value, right? If you take an absolute value of a product, that's the same thing as the product of the absolute values, right? So allow me to take the absolute values of these things individually. Oops. Okay. So I haven't done anything. It's still the same statement. Okay. Now, we knew that the a sub n were bounded, right? Right. So that is that the size of these terms are all controlled by some number m. Let's say that m is the bound of the a sub n's. So let's say that capital N note. A bound on the size of the a sub n's for all n. Okay. We know that they're all smaller than some number. Okay, so we can replace this thing by m times the sum here, so p from here to here, b sub n minus b sub n plus 1, plus b sub q plus b sub p. Right? We just factored out the m. Right? Each of these things is smaller than m, so we replace them by m, and then we factor it out. Okay. But now recall that these numbers, the b's, are decreasing. Right? So if we're subtracting the next guy from the previous guy, then this is a positive number. Right? So I can get rid of the absolute values. Right? Further, they're decreasing to 0, so they're all positive numbers, right? Or at least they're all non-negative numbers, right? So I can get rid of the absolute values everywhere, right? All these things are positive. All these things in the absolute value are positive, right? So I get m, and I get summation b sub n minus b sub n plus 1, right? From p to q minus 1. And I also have a b sub q, and I have a b sub p. Okay. But you see what's going to happen? Questions? Okay. You see what's happening here? We're going to have b sub p minus b sub p plus 1. And then we're going to add on b sub p plus 1, subtract off b sub p plus 2, and so on and so forth. Right? So this is a telescoping series. Right, it's going to collapse. Do I need to write that up? Right, this is going to be b sub p minus b sub p plus 1 plus b sub p plus 1 minus b sub p plus 2 plus minus etc. Right, and then the very last term is going to be b sub q minus b sub q minus 1 minus b sub q, right? And then these terms collapse, right? All these terms in the middle cancel each other out. I'm just left with a b sub p minus a b sub q, right? So that's this thing here, right? So in the end, you see what happens. I get m times b sub p minus b sub q plus b sub q, which cancels, plus b sub p. Okay. So in the end, I get 2b sub p over m. Times m, sorry. Thinking to the next step, sorry. Times m. Right? Okay, so remember what we had to do. We were trying to choose the right n to make this smaller than epsilon. Right? So what n do we need to choose? Right? So let me write it just over here. So then, so choose n such that b sub p, such that b sub n is smaller than epsilon over 2m. Right? Right? Because b sub p, p is bigger than n. P is bigger than n, right? So we know that then this 2b sub p times m is less than or equal to 2b sub n times m, right? Because b sub p is, you've got a decreasing sequence, right? And b sub n occurs before b sub p, right? Right? And we know by what we just chose this, we know that this is smaller than 2e over 2m times m, right? Which is epsilon. Right? Why could we do this? Why could we choose an n such that this happens? Why is that okay? Why do we have the right to do that? James?
Because bn goes to 0.
Because bn goes to 0, exactly. Right? Bn decreases to 0, so right, this is some positive number. Eventually, it's going to be smaller than, right? And m is a constant, right? M is some constant, so we know it's going to be smaller. Okay. Okay. Any questions? Okay. So this is pretty straightforward thinking. Once you have the technical lemma, right? Once you have this technical lemma, right, you say, okay, I've got this thing. I'm going to somehow try to bring in, right? I'm going to bring in these partial sums, right? Because I have some condition on the partial sums. Partial sums are bounded, right? So I'm going to rewrite this thing with some expression that involves the partial sums, right? Then I just do the triangle inequality, use the conditions on B, and see that what n do I need to choose. So I hope this is obvious, like what you would need to do, at least in hindsight. It's of course not obvious, if it's just given to you cold. But I hope you understand what we're doing. Okay. Okay, so let me erase here. Okay, let me erase here and put up a consequence, which is Leibniz's theorem. So this is the so-called alternating series test, right? Alternating series test, right? So yes, you can prove this in other ways, but we've got this powerful tool, and we're just going to use it to get a bunch of results. Okay, so you probably know Leibniz's theorem. So it goes like this: right? You have some sequence of numbers. Okay, and those numbers are alternating in sign, right? So like so C. Let's say that the odd terms are non-positive, and the even terms are non-negative. So they're alternating in sign, or maybe they're zeros, it doesn't matter. Okay. And you have a couple of conditions that the sizes of them are decreasing. Right? So the magnitudes of the terms are decreasing, and they are decreasing to 0. Okay. So keep in your mind, for example, something like -1 to the n over n, right? The alternating harmonic series, right? So you've got the sign of the terms are alternating. It's decreasing in size, decreasing in magnitude to 0. Okay. This converges because of the alternating series test. So that's. Okay, so if these three conditions are satisfied, then their infinite series converges. Okay, and the proof is just apply the previous theorem, right? So let a sub n be -1 to the n, right? Let b sub n be the size of c sub n, right? Then a sub n, b sub n is just c sub n. Right? And summation a sub n, b sub n converges by the previous theorem. Right? We had this previous theorem that talks about sums of products. Okay. Well, this thing here is a product. Right? It's a product of this. It's a product of -1 to the n times 1 over n. Right? Now, so this is our Our a sub n's, remember, are going to be the sums of the a sub k's as k goes from 0 to n. It's the partial sums of the sequence, partial sums of the series. Right? Where you're just summing -1 and 1, -1 and 1, -1 and 1, -1 and 1. That's a bounded sequence, right? This partial sum sequence is bounded, right, by 2. Okay, right? And we have that the terms are decreasing to 0, right? The terms are decreasing and to 0. So we just apply the theorem, and that's that. Okay, everyone all right? Maybe it's not that interesting. Okay, let's do another thing, which is going to be better. I'm gonna keep this up because we're going to use it again. Okay, so here's another theorem, and this one's about power series. So suppose that summation c sub n z to the n is a power series with radius of convergence equal to 1. Okay. So you have a power series. You know that it converges in the unit disk. Okay. So we're going to, just as before, we're going to use the theorem. So if the if the coefficients are decreasing to 0, oops, right, and they're decreasing, if the coefficients are decreasing and they decrease to 0, then in fact the power series converges in the closed disk. Excluding the point 1 itself. Okay, so what this is saying is that you've got this power series, the coefficients are decreasing, they decrease to 0, and you know that it has a radius of convergence of 1. In fact, it converges on the boundary as well, excluding this point 1. Okay. So it tells you about the boundary behavior of your series. Okay, so maybe this is kind of a contrived example, but we can use the previous result to get this. Okay, so as you might expect, we're going to let a sub n be the z's, right? Let a sub n be z to the n. Right? And we're going to let the b's be the coefficients. Okay, of course, right? Because they're doing what we need them to do, right? They're decreasing to 0. Okay. So what we will have to worry about is boundedness, right? So we want to show that that summation a sub n, b sub n converges on the boundary, right? On the boundary, excluding the point 1. Okay, so this notation means excluding, right? So you have a set, right? You have the set of all points in the complex plane whose size is 1, but we throw out 1 itself. Okay, so so what do we need to do? We need to show that that the partial sum is bounded, right? So consider the partial sums, right? A sub n, which is the sum of the z to the k from k equals 0 to n. Okay. Do we know anything about this? Yes, right. This is the partial sum of the geometric series that we saw a day or two ago. Right. So this is going to be, we have a formula for this, right? We worked it out. This is summation, 1 minus z to the n plus 1 over 1 minus z. Right? So, sorry, let me put in something here. So fix a z in that set, right? Let's call this set E. Okay, the boundary excluding the point 1. Right? We want to show that this thing converges at that point. Well, in order to do that, we have to show that this thing is bounded. Okay. So why is this bounded? Why is this bounded? Right? Why is this bounded for all n? Well, could use somebody said it. Nobody? We can use the triangle inequality. We can use the triangle inequality. We say, okay, well, this is smaller than 1 plus this thing over this thing. I thought I heard somebody mutter triangle, but nobody's willing to own up to it. Okay, right? Right. The top is of course smaller than this top, and the bottoms are equal. Right? Okay. But remember where z is. Z is on the boundary, so we know that this is 1. Right? This term is just 1 to some power. Right? So we get this equals 2 over this constant. Right? Z was a fixed point. Z was a fixed point. We don't have to worry about z moving around. Right? We're fixing a z and saying, does this power series converge for that z? Right? And it does. Right? Because these the a sub n's are bounded, but these guys are decreasing to 0, and we use the previous theorem. Okay, how's everybody doing? You seem kind of sluggish. Or are you tired? You are tired. Okay. I didn't know what to say to that. During my first semester of college, my father sent me an article, like a Xerox of an article, about an engineer who slept only 3 hours a night. So this guy, he slept only 3 hours a night, and it talked about all the amazing things he had done with his life. He had gotten multiple advanced degrees. He was a pilot. He did this and this, and I thought, wow, I want to be like this guy. So I started sleeping 3 hours a night. This was a huge mistake. I did really poorly my first semester in college. After that, for the rest of college, I slept exactly 7 hours a night, from 12:30 to 7:30 every single day. Yeah, that worked a lot better. Yeah. Okay. So, okay. So there is an example. I don't know. Let me just throw this example out. Right. If we have the power series z to the n over n. Okay. If you look at this thing converges in the unit disk, and by this theorem, you see that it converges on the boundary as well, except at 1. Right. At 1, you get the harmonic series. It diverges. I think that was actually the appropriate time to leave the class. Okay. Because we're going to do a couple of not so interesting things, and then we'll get to something more interesting. So if you want to leave the class, this is the time. So absolutely convergent series. Absolutely convergent series. Okay. So, what's an absolutely convergent series? Is anybody willing to say what an absolutely convergent series is, if you remember? nobody's willing to. Either you've all forgotten or nobody's willing. It doesn't matter. Yes, Eric?
Is it just like for within the series, you take the absolute value of it, like
Yes.
even if it's negative, and
Yes.
then the absolute value converges?
Yeah, you start off with a series. So you have a series. And if the sum of the absolute values converges, then we say that, that this thing converges absolutely. Okay. Okay. So it converges absolutely. Does it actually converge? Does this thing actually converge itself? Do you remember? So we say if this thing converges, then we say that the original guy converges absolutely. Does the original guy actually converge? Yes. Yes, it does. Yes. Yes. That's okay. In the proof, maybe I'll let you try it. So the proof involves the Koshi Criterion. So take 2 minutes, say, and write down what the Koshi Criterion would be for this and for this, and you'll see why the Koshi Criterion for this implies the Koshi Criterion for this. Okay, it's a good exercise. By the way, those of you who wanted to learn martial arts from me, I think I will teach a class and teach it in the flip manner that you suggested. Like have you guys learn how to roll, and then you can come in and I can show you everything else. So, yeah. Okay, let's get to it. The claim is that if this thing converges, then this guy converges. Okay. So start off, we say assume that this thing converges. Right? And we want to show that for every epsilon greater than 0, there exists an n such that if n and m are bigger than n, then summation a sub k from k equals m to n is smaller than epsilon. Right? That's the Koshi criterion. Okay. now we know that this thing converges, right? So we know that this guy's Koshi criterion is satisfied, right? We know there exists some n such that if n and m are bigger than n, then this thing is smaller than epsilon, right? So what do we need to say? By the triangle inequality, we are done. Okay. So just use that n. Just use that n. That, and let's call it n naught, say. Just take n to be n naught. Right. Then this thing is certainly smaller than this thing, right, which is smaller than epsilon. Right? Okay. So, okay, so, okay, everybody's okay with that, I hope? Right, so converges absolutely, right? If something converges absolutely, it converges, but it's even better than that, right? The sum of its absolute values converges, right? So this is an even stronger condition, right? Right. So you can think that, you know, the absolutely converging series are a special class of the converging series. Okay. That's how you want to think about them. There's a comment in the text that we shall see that we may operate with absolutely convergent series very much as with finite series. That is, you know, for absolutely convergent series, it's pretty much like adding numbers, the same sort of addition that you do in elementary school. Whereas for non-absolutely convergent series, you can run into trouble if you try to do things like you did in elementary school. Let me give you an example. I think we have enough time. So let me just do a quick example of how things could go wrong. So let's start off with sort of your standard non-absolutely convergent series. Right? This is the alternating harmonic series. It does not converge absolutely, right? Because if you take the absolute value of these guys, you get the harmonic series, which doesn't converge. Okay. So, but by Leibniz's test, it does converge to some number, right? As we said before. So let's call that number gamma. Okay. Now, I'm in elementary school. I think, okay, that thing converges. I'm going to multiply it by a constant. That's actually okay. So my elementary school instincts are all right so far. It's all right to multiply, right? When you multiply a series by a constant, if it's convergent, then it's the same thing as the sum of the constant times the terms, right? So, but let's do that. Okay, so let's take half of it. Okay, so again, you know, I'm still in elementary school, and I think, well, I've just got a bunch of numbers here, and I'm gonna add these two things together. What is 3? I want an expression for 3/2 gamma, right? Okay, so I said, okay, well, I can cancel things, right? So I'm just going to cancel those guys, right? I got this, that's 0. I've got this 1 here. I've got a minus a fourth. I've got another minus a fourth. I'm going to just add those guys together. I get minus a half, right? So those guys are, that's taken care of. Those guys are taken care of, right? I've got this third here, right? I've got this third here. The sixth, I see they get rid of each other. I've got minus an eighth. I've got minus an eighth over here, so I've got 2 of them. So I get minus a fourth. Right? I also have this fifth here, so I get 1/5, right? And so on and so forth, right? You see what's going on. I've got a minus a 12th here, another minus a 12th, that gives me minus a 6th, right? I've got the 7th, I've got plus a 7th, I get minus an 8th, plus a 9th, etc., etc. Right? Right? But you see what that is? That's the same thing that I started off with, right? So 3/2 gamma equals gamma. Gamma is some non-zero number. It's not 0, that's for sure, right? So I divide both sides by gamma, and I see that 3/2 equals 1. In other words, 3 equals 2. Okay, so you see that if you do things without thinking about convergence of partial sums, right? Convergence of partial sum series, and instead of thinking in terms of partial sums, but thinking as if you could sort of take these things out of order, right? Try to take things out of order. I'm gonna jump around a bit. I'm gonna take this one and that one and add those guys together, right? I rearrange. If you do what's called a rearrangement, then actually you run into a lot of trouble. Okay, and then there's a theorem. We're not going to do it, but there's a theorem in Rudin's book that says if your series is convergent but not absolutely convergent, then you can create rearrangements that converge to whatever you feel like. Any number that you desire, you can rearrange it and get that number. Okay, so yeah, so it's dangerous. And there's, of course, there's a theorem that says if it's absolutely convergent, then that doesn't work. No matter how you rearrange it, it will converge to the same thing. Okay. That's what's great about absolutely convergent series. Okay, so that was just entertainment. I show that even in a top 2 class. Okay. Okay, a couple, just sort of a side comment first. So I'm not going to prove the following theorem, that if you have one series that converges to A, and you have another series that converges to B, then the series of the sum of the terms converges to the sum of the limits. Right? Nor am I going to prove the theorem that I just mentioned, that the sum of CAN is going to be C times A. Okay, I'm going to leave those to you. Okay, and those are true for any convergent series. Doesn't have to be absolutely convergent. Any convergent series will do that. Okay. What we're going to spend the rest of the class on is something called the Koshi product. Which is, you want to think of as sort of like the product of 2 series. Okay. Okay, so here's the definition. You have 2 series, A sub n and B sub n. Okay. Let C sub n be the sum from 0 to n of A sub k, B sub n minus k. Okay. We call the series, summation C sub n, the Koshi product. of these two series, A sub n and B sub n. Okay, the picture you want to have in mind is the following. So you have, okay, you have your, actually let me just take the partial sums and multiply the partial sums of these two series together, right? Well, you're going to have A naught, B naught, A naught, B1, A naught, B2, A naught, Bn, right? You're going to have A1, B naught, A1, B1, A1, B2, right? A1, Bn, right? And so on and so forth, right? So you're going to have so then you get an B naught to an Bn. Right? Okay. So you get all these, the sum of all these terms. Right? Okay. So right, and if we're thinking about like the product of the infinite series, right? Then we don't stop at n, but actually we get this infinite, we get this infinite, infinite matrix here of terms. Okay, and so the Koshi, you see what this thing is, right? C0 is just A0, B0. C1 is A0, B1 plus A1, B0, A1, B0, right? It's the sum of all terms where the indices sum to n, right? The sum of all the terms, all these products where the sum of the indices is n. Right? So C0 is this thing, C1 is this thing, right? C2 is this, and so on and so forth. Okay, so you're just taking, where C sub n is basically taking all these terms and then summing by taking this and then adding on the second term. This is C0, C1, C2, C3, and so forth, so on and so forth. Okay? Okay. Okay, so Cn is the sum up to this point here, right? So you get this the sum of this upper triangular thing here, right? Cn is the sum of this upper triangle. Okay. Okay, so remark, it's not necessarily true that if the series converge, then the product converges. Okay, and there's an example, a counterexample to that on page 73. I'm not going to go over it. So that doesn't necessarily work out, but there is this theorem by Mertens. I'm not sure how to pronounce this. Mertens. That tells you about convergence of Koshi products. Okay, so here it is. So same notation as before, right? You have two series, each of them converges, right? So one series converges, both of these series converges, and you let C sub n be the Koshi product, right? then here's the theorem that if one of these converges absolutely, then the sum of the C sub n actually is the product. Okay. Then the Koshi product actually is the product of the limits. So give me a second to make sure I understand what's going on. Okay, okay. Got it, throwing everything out of order. Okay, so this is a pretty cool theorem, and I think it's kind of instructive to think about how Mertens kind of would have thought about it. Okay, so let's think. Right, we're gonna introduce some notation. So some notation first. As before, capital A sub n is going to be the partial sum from k equals 0 to n. Similarly for B sub n and C sub n. So similarly for the other two guys, these are just the partial sum notation. Okay, and we're going to let beta sub n denote bn minus d. Okay, so it's how far the partial sums are away from the actual limit. Okay, so it's like the error of B sub n, if you want to think about it that way. Okay, so right, so we're hoping, right? We're hoping that the C sub n's converge to AB. Right, that's our goal. That the partial sums of the Koshi product converge to AB. Okay, so let's think about it. Let me come back over here. Let's have this already drawn. Okay. So the sum of this upper triangle is C sub n. Remember, right? So let's think about what it is by summing vertically. Okay. So here we get A naught times the sum of B naught to Bn. Right? Right. So this thing is C sub n, right? And we're hoping that it converges to AB. Okay. So, right, this thing is A naught times the sum from B naught to Bn. That is the partial sum B sub n. Right? This guy is A1 times the partial sum, not all the way to Bn, but to Bn minus 1. Right? So you get A1 partial sum Bn minus 1, A2 partial sum Bn minus 2, An partial sum B naught. Okay, so that's actually our C sub n. Okay, so now we know that we're hoping to get, so this is sort of our scratch work over here, right? We want to get AB. Right? We want to get AB. So what I'm going to do is slide in a B. Okay. I'm going to replace these guys by B. Okay. Right. B sub n is of course B plus beta sub n. Right. So that's what I'm going to do. I'm going to replace these guys by B plus beta sub n. So A naught B plus beta n plus A1 B plus beta n minus 1, excuse me, plus AN B minus beta 0. Okay, and you see what you get there is you get that Cn equals B times capital A sub n. Right? I'm going to take just the terms involving B's. Right? And I got the sum of A naught through An. That's the partial sum of the A sub n's. Right? All of them times B. So I get that thing. And then I get this kind of funny term. Right? I get plus A naught beta n plus A1 beta n minus 1 plus An beta naught. Sorry, this should be a plus here. Okay. Okay, so this is good, right? Because I know that that the A sub n, if I can show that this thing vanishes, right? If I can show that this thing vanishes, then I'm done, right? Because the A sub n is the partial sums that will converge to A, right? So that will tell me that the C sub n's converge to AB plus 0. Okay, so that's my goal. Okay, so just calculation yields this thing here, right? We have this expression for C sub n, and let's call this thing gamma. Not the same gamma as before. It's just using the same. I think do they call it? I'm sorry. Gamma n. Of course, because it depends on n, right? And we're hoping that gamma sub n converges to 0 as n goes to infinity, right? So it suffices to show that that the limit of the gamma sub n is 0. Okay. Okay. So I'm going to erase this thing. Okay, and here's where the absolute convergence is going to come in handy. Okay. So claim the limit of the gamma sub n is 0 as n goes to infinity. Right, and proof. Fix at epsilon greater than 0. Okay, and okay, I'm gonna just lay it out for you rather than because we have limited time. I'm just gonna lay it out for you. Okay, so let alpha be the sum of the absolute version of the series, the sum of the absolute values of the A sub n's. Okay, right. We know that it converges. Let's say that let this alpha be the limit. Okay. Okay. Now, remember what the beta sub n's were. They were the error. Those guys go to 0, right? Because the B sub n's converge to B, so the beta sub n's go to 0, right? These guys go to 0, right? Because the B sub n's, the series converges. So we know that there exists a point such that past that point, we have some control on the size of the betas. Okay. So we're going to make all the betas smaller than epsilon. Okay. So this should be kind of mysterious because why are we doing this? It'll become evident when we start thinking about what we actually need to do. Okay, so think. If we look at the size of gamma sub n, right, that's of course, a naught bn plus an b naught, right? But we can make that, sorry, give me 1 second to think here. Yeah, okay, sorry. So think, look, we have this capital N, right? We have this capital N, so we're going to break this into two parts, right? The terms with beta, where beta has an index greater than n, and the terms where it's less than n. Okay, so let me write that out. That's alpha a naught beta n plus a1 beta n minus 1 plus dot 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 a sub n minus capital N minus 1 beta n plus 1, right? Plus a n minus capital N beta sub n plus a n beta naught. Okay, so I'm just breaking it. I'm just pointing out that there's some point, there are terms where the index on the beta is big, right? I'm going to use the triangle inequality and just break this into two parts. Okay. The terms where the index on beta is big and the term where the index on beta is small. And notice that there's a finite number of terms here. Okay, right? There's finitely many terms here. Finite number of terms. Right? That n is a constant. That capital N is a constant, right? So there's just this thing here. This part will increase in terms, right? As n gets big, this will have more terms, but this part won't. Right? This is just a finite number of terms. And then the good thing about here is that the betas are small. Right? Okay. So what do we get? We get that, well, look, right? All of these betas in absolute value, are small. Right? So, what we really do is we take the absolute values of each of these things, and then notice that these things are all smaller than epsilon. Right? So we get epsilon times the sum of the absolute values of the a sub k from k equals 0 to n minus 1. Right? And then we have this leftover term here. Okay, but this thing here, we have control over, right? This is where the absolute convergence comes in, right? We're taking the sum of the absolute values. Well, that's controlled by alpha, right? So this is controlled by epsilon times alpha plus this thing here. Okay. 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 So now think as n goes to infinity, what happens to this thing? We have a sub n times b naught. We have a sub n minus capital N. So there's this sort of range of terms, right, from n to n minus n, and that range goes off towards infinity, right? All of those things go together at the same rate towards infinity, right? This thing converges, so you know that these guys converge to 0 by the divergence test, right? Convergence of a series implies that the terms must go to 0. Yes, right? So all these terms go to 0. There's only, right? You get these terms go to 0. They're multiplied by these constants. Well, that whole thing is going to go to 0. Okay, right? So what does that tell you? That tells you that the limit of this thing is smaller than epsilon times alpha, right? Because this thing went to 0. Okay, but epsilon was any positive number, right? Epsilon was arbitrary. Epsilon was arbitrary, right? Was an arbitrary positive number. So for this to be true for any positive number, the only way that could be true for any positive number is if the limit is 0. Right? We can get any positive number over here on the right side, right? The limit of the absolute values is less than or equal to any positive number, right? So that tells you that the limit of these guys is 0. You guys don't look as happy as I thought you would be at this point, but I guess that's okay. Okay, that's it for today. If it's confusing, don't worry. As I said in my other class, or maybe this class, I never understood anything that my professor said, but I always went home and thought about it, and then it became clear. So, yeah.